Hey everyone, this video is going to go over section 5.1, numerical differentiation. The file for the handout is posted in Blackboard. Okay. So basically what we're going to do here is numerically take derivatives by using what are called finite difference formulas. Okay. So often in science and engineering, we're going to have data points that are going to be representative of a function, but we're not going to necessarily know what our function f of x is. So what we do to approximate the derivative without knowing the function is use these finite difference formulas. There are a few different types of difference formulas that we'll deal with. One's called a forward difference, which uses a particular point and a point that's has a larger x coordinate, a backward difference, so the point and another point that has a smaller x coordinate, and then the center difference formula, which basically uses 2 points around the point at which we want the derivative, and will approximate the slope of that tangent line that way. So if we have data, normally what we have to do, we can use center difference formulas for any point that's in the interior of the data set, and at the end points of the data set we have to use a forward or backward difference. So let's take a look at the first one. So here we're going to look at the 2-point forward difference formula. That is this guy right here. Okay. So we're going to generate this using Taylor's formula. So let's just recall Taylor's formula. So here we have section 5.1. Numerical differentiation. So let's recall Taylor's formula. So from section 0.4, we looked at a formula that would be utilized to approximate the function centered at various points. That formula was this. We know that Taylor's formula represents any function f of x as a polynomial. So the sum of a bunch of polynomial terms. That formula was sigma I goes from 1 to, let's say, k of the ith derivative evaluated at some c divided by I factorial times x minus c to the I. Excuse me, this should be 0. So here's the formula for Taylor's formula. We can actually manipulate this a little bit if we consider a shift in x a bit. So f of x plus c is equal to sigma I goes from 0 to k of f ith derivative at c over I factorial times, now we're going to substitute in x plus c for x, so this just becomes x here to the I. We can also kind of rearrange things a little bit. Therefore, f of h plus x is equal to, so we're just going to swap the x's and c's here for h's and x's respectively. So I goes from 0 to k, the ith derivative of, now the c becomes x over I factorial, and x becomes h h to the I. Okay? This is going to set up for what we need for the forward difference. So this is, if we consider I to be 0, this would be the 0th derivative of f, which is just f. So f of x over 0 factorial is just 1, so I'll put that. And then h to the 0 is also 1. So the first term will just be f of x plus, now I is 1, so f prime of x over 1 factorial, which is just 1, times h to the first power, so h there. Next term would be when I is 2, so f double prime of x over 2 factorial, h squared, so on and so forth. So the second to last term would be the k plus k, or the last term would be the kth derivative of x over k factorial times h to the k. And then the very last term, our error term, recall, was the very next term. So the derivative there over k plus 1 factorial, h to the k plus 1. And actually we can say that this is c. Let's call that c. And c is between x and x plus h. Okay. So what we can do is generate the 2-point forward difference formula using this equation, right? So if we consider, so for the 2-point forward difference, formula, we want to derive this formula here, right? So what we're going to do is take our formula for f of h plus x, or x plus h, same thing, and we're going to try to solve it for f prime, okay? So here we're only going to go out to, let's say, two derivatives here, right? So f of x plus h is equal to f of x plus h times f prime plus, I'll go one more term. So this will be our error term here. So let's say h squared over 2 factorial times f double prime at c. Okay? Again, c is between x and x plus h. Okay? Now if we manipulate this a little bit, just rearrange some things, we can get f prime solved for. Okay? So I'm going to take everything over to the left-hand side besides this term. So we can get f of x plus h minus f of x minus h squared over 2 f double prime at c equals h f prime. And then dividing through by h, we'll get f prime of x is equal to this difference divided by h, so f of x plus h minus f of x all over h minus, now we're going to divide this term by h as well, so we're going to reduce this power by 1. So this will become h over 2 f double prime at c. Okay. So you can see that the derivative is approximated by this term right here, minus some unknown error value, right? So f prime can be approximately denoted by this 2-point forward difference like that, okay? So basically, what does this mean? What does this boil down to graphically? Well, let's take a look. So here, note that we can graphically solve this. So let's say we have x here, and x plus h, we're just going to consider h positive. X plus h there. And let's say we have this curve. Okay. So we have points x and a point at x plus h. So that means that this y value would be f of x, if this is y equals f of x. And this y coordinate would be f of x plus h. So recall that the first derivative at x is simply equal to the slope of this tangent line. We draw it carefully. Slope of this tangent line is equal to f prime. So here, m for this is f prime of x. So what we're doing is using this secant line, so that's what this formula is, right? So this is the change in y at y2 minus y1 over x2 minus x1. Well, x plus h minus x is simply h. So we're utilizing the slope of this secant line here. The slope of this line is f of x plus h minus f of x over h, which is approximately equal to f prime of x. Right? So these two slopes are approximately equal to one another. Now, the approximation gets better if h is smaller, right? If we push this point back towards the point at which we're trying to find the tangent line, this guy approaches this guy, the slope, that is. Okay. So that's what we're getting into, just a simple, you remember from Calc 1, that kind of thing. Okay. So let's do an example. So we want to use, actually, let's take a look here. There's also the 2-point backward difference formula, which is f prime is f of x minus f of x minus h over h minus h over 2 times the second derivative at c, right? The error term there. So basically what this does is just kind of interchanges these points. Instead, here would be your x, here would be your x minus h. We'd be doing the same kind of thing as we are here, except you would be using a point behind x rather than, so let's say this was x minus h there. We'd be using this slope to approximate this guy right here. Okay? So same idea. So the derivation is left as one of the assignment problems for 5.1. All right? And also, we call this an order 1 method, or first order method, because the error term is proportional to h to the first power. So here's our error term. We look at the power on h, and that gives us the order of our finite difference formula. Okay? So here we would have order 1. We can create order 2, order 3, or order 4 difference methods, as we'll see shortly. Okay? So this would be, so the 2-point forward difference is a first order finite difference formula. Okay? So example 1, we want to use the 2-point forward difference formula with h equal to 0.1 to approximate the derivative of f of x equals 1 over x at x equals 2. You want to compare the actual error with the theorized error from the formula. Okay? So let's do that. So the first thing that we need to do is calculate that forward difference, right? So we know that f prime of 2 is approximately equal to, let's just fill in our formula values there, f of 2 plus 0.1 minus f of 2 over 0.1. Well, what is f of 2 plus 0.1? That is f of 2.1. So that would be 1 over, for our function, 1 over 2.1, because our function is 1 over x, right? Minus 1 over 2 all over 0.1. Okay. So this is approximately equal to, if we use our calculator, negative 0.2381, so 4 decimal places. Okay. So this is the approximation to the derivative of this function at 2, using the 2-point forward difference formula. Okay. Now let's investigate the error. How good is this approximation? Well, we know we can just find the derivative of this function. What is f prime of x? Well, that's the derivative of 1 over x. That is negative 1 over x squared. All right? So f prime at 2 is exactly equal to negative 1/4 or negative 0.25. So the actual error is the absolute value of our solution minus our approximation. Right? Here we're not using norms because we're just dealing with a single value, not a vector. So let's see, if we do that, we will get 0.0119. So the error is relatively small, I guess. Now let's look at the theorized error. The theoretical error is equal to, well, let's look back at our error term here. You notice our error term is h over 2 times the second derivative at some c value within the interval x to x plus h, right? So we know that this is h over 2 times f double prime at c, which would be our h, which is 0.01 over 2, times, well, what's the second derivative of this function? That is 2 over x cubed. Okay. So 2 over c cubed, that is. This is f double prime at c. So we get 0.1 over c cubed. So it just depends on the value of c, but we know that c is in between 2 and 2.1. So the theoretical error is between the two values 0.1 over 2.1 cubed and 0.1 over 2 cubed. Of course, this guy is going to be a smaller number than this one because the denominator will be larger. Okay? So if we calculate that, do that in your calculator. Let's see what we get. So we have 0.1 divided by 2.1 to the third. Let's see that. bit off. Anyway, you'll have to believe me. So 0.0107 is less than theoretical error, which is less than 0.0125. So we know that theoretically the error should be between 0.0107 and 0.0125. Is our value in between those two? It is. Okay? All right, so that is the the basic ones, 2-point backward difference formula. Forward difference formula. We could also do this for the backward difference formula in a similar fashion. Okay. Now let's look at the 3-point center difference formula. So here, if we look, what we have going on here, the f prime is equal to this finite difference formula minus this error term here. Okay. So let's see about what that means and how do we get there. Okay. So if we look back at a graph, say our x is here this time. So we have an x plus h right here and x minus h over here. Okay. Of course, h is the same, so they should be the same distance away. All right. H here and h there. Let's draw our curve again. Something like that. So this time we have 3 points. We're concerned with finding the slope of the tangent line at this point, at x, right? We want f prime at x. And we're going to utilize the 2 points that are surrounding it, right? So here's 3 points. 3-point centered difference gives us the approximation to the derivative at that center point. So again, we're looking for the slope of this tangent line here. That would be the derivative at that point. And we're going to utilize the secant line that goes through these 2 points. So you can see, just by comparing it to the last one, you can see that this is a bit of a better way to do things, right? So these 2 lines are nearly parallel to each other. So that's actually a better approximation than what we had last time, right? Because if you notice here, these are not quite parallel to each other, right? So the center difference formula actually gives us better accuracy for the approximation. And you can see that here with the error term. If h is a very small number, when you square it, it gets even smaller. So that square gives us a second order method, which is a better approximation because it reduces the amount of error that we see. Okay? So what is the slope of that purple line there? Well, m would be equal to y2 minus y1. Well, y2 is f of x plus h, and y1 would be f of x minus h. So y2 minus y1, f of x plus h minus f of x minus h over this distance here, x plus h minus x minus h. That gives us 2h, right? That's an h there, that's h there, 2h. And this will be approximately equal to f prime at x. That's x there. So let's derive it using our Taylor formula here, okay? So derivation of 3-point centered difference for f prime. All right. So if we take a look here, we're going to need two things this time. So we're going to have our f of x plus h. We're also going to have f of x minus h expanded using a Taylor's formula, which is not too bad to do. So let's consider f of x plus h. We've already seen that once. So that was f of x plus h f prime of x. Now in the previous one we stopped at the second derivative here, when in fact we actually need to go to the third derivative because the order of this finite difference formula is actually higher. So we need to go out to 3 derivatives. So I'm going to add an extra term. So we'll have h squared over 2 factorial, or just 2, f double prime of x plus h cubed over 3 factorial times f triple prime at c. That's going to be our error term. Okay. We also need f of x minus h. This one's similar, except we're going to have some sign alternation. So every time we have an h, it actually will become negative h, right? Negative h, so that's going to make a minus there. Negative h squared is still going to be positive, and then negative h cubed is going to be negative. So we're going to have some sign alternation on this one. Same terms, but with alternating signs. And since this c is in between, so here c, let's call this c1. All right, so c1 is between x and x plus h. Okay. Here we're going to have a different c because we're centered at a different location. So this one's going to be in between x minus h and x. Okay. All right, so what we want to do is when we're developing a finite difference formula, we utilize all of the known values of f that we want, and we try to create something that has so again, we're going to solve this guy for f prime. We're going to have an error term that is of the third derivative. So we want to get rid of these second derivative terms here, right? The error terms are fine, but these second derivative terms need to go away, right? We're only trying to get something in terms of f prime. So what we can do is take each of these equations and subtract them, right? So if I take f of x plus h minus f of x minus h, these two terms are going to cancel, okay? Not only those, but these f of x's will also cancel. All right, so let's see what we get. So let's look at f of x plus h minus f of x minus h. What's that going to be? So here we're going to take this term minus this term. So f of x, take away f of x is 0. hf prime minus negative hf prime will give us 2hf prime. H squared over 2f double prime minus h squared over 2f double prime is 0, so those go away. And then we'll have h cubed over 3 factorial f triple prime at c1 minus negative h cubed over 3 factorial f triple prime at c2. Okay, so what I'm going to do, since they both have this term h cubed over 3 factorial, I can just factor that out. So I'm going to have plus, so it'll be this guy plus this guy. So I'm going to factor out that h cubed over 3 factorial. And then I'll have the sum of these two terms here. F triple prime c1 plus f triple prime c2. Okay. Now, so we're almost there, right? So we know we can just divide this 2h over, we'll get our f prime there. what we need to do is fit this to what we're trying to get, right? So we're trying to get h squared over 6 times f triple prime at c. So if you look in your book at theorem 5.1, by theorem 5.1, so I'll put that there. I'm not going to go through the proof of that theorem. It's just basically an intermediate value theorem. It says that the sum of two function values can be gathered by some multiple of the function evaluated at some point within C1 and C2. Okay, so I'm going to fudge that a little bit. So we'll just write this. It's 2h f prime of x plus h cubed over 3 factorial f triple prime of c. Okay? So c is going to be some number between c1 and c2. So again, that's by theorem 5.1. You can take a look at the proof in the book. Okay? So what we can do is just rearrange some things here. Take the error term to the left. So we'll have f of x plus h minus f of x minus h minus h cubed over, well, 3 factorial is 3 times 2 times 1, so that's 6 f triple prime at c equals 2h f prime. So dividing both sides by 2h, I'll get f of x plus h minus f of x minus h over 2h minus, oh, excuse me. So here, so here with this guy, actually, this would be 2 f triple prime. So like if we let h go to 0, these guys become arbitrarily close. So we can consider these as being the same value. So we'd actually have 2 of those and 2 of those. Okay. So when we divide by 2h, the 2's will cancel, and we'll be left with an h squared there. Equals f prime of x. Okay. So once again, all I've done here is move the error term over and then divide by that 2h. So I'm going to group this term because that's my approximation. So that's all over 2h. And then when I divide this guy by 2h, I'll lose the 2 and I'll lose one of the h's, so h squared. Okay. So f prime of x is approximately f of x plus h minus f of x minus h over 2h. Right? And again, what would the order of this finite difference method be? Well, the error is proportional to h squared. Therefore, this is an order 2 method. This is an order 2 method. It actually produces less error. It's better at approximating, as we saw with our graph. Okay. So let's verify that it's better at approximating. We want to do the same problem as last time, but using this approximator instead of the 2-point forward difference, right? So let's look. So example 2. So f prime then at 2 would be approximately equal to, let's just fill in our formula, f of 2 plus 0.1 minus f of 2 minus 0.1 over 2 times 0.1. Okay. So let's see what we get there. That'll be 1 over 2.1 minus 1 over 1.9 over 0.2. And that rounded to 4 decimal places is negative 0.2506. All right. So you can see that our error, actual error, is equal to 0.25. That was the exact value of the derivative, minus our approximation, which you can see is 0.0006. So it's about 3 times less than the previous error. Okay? So here we see the error is less than that of the 2-point forward difference. Okay. This is because the 3-point center difference is order 2, higher than the forward difference method. Okay. Now you can see where we can get into some trouble with this because we are subtracting values here. So this is just a note on convergence. We need h to be relatively, we can't just let h go to 0 here, right? Because if h went to 0, these two values would be nearly equal, and we would lose significance like we saw with that floating point representation in Unit 1. All right, so we can also look at finite difference formulas for creating higher order finite difference methods, okay? So here are just some examples of various Taylor expansions. I've just given you these formulas. We've dealt with this one today. In order to get a higher order formula, we would need to go out further and actually have more terms, right? So if, like, say, we wanted an order 4, we would need to go out to 5 terms and do the same kind of analysis we just did. So here is f of x minus h out to 5 terms. Here's f of x plus 2h. So instead of having just h at each of these values, we would have 2h and 2h squared and 3h squared cubed, 2h to the third, 4h to the third, 5h, So here we would have f of x plus, so this would be 2h to the first power times f prime. This would be 2h squared times f over 2 times f double prime, 2h to the third, 2h to the fourth, 2h to the fifth. Likewise here, negative 3h just replaces all those h's. So negative 3h to the first, negative 3h squared is 9h squared, negative 3h to the third is minus 27h cubed, so on and so forth, right? So this is how we just expand using various different Taylor expansions. So we can do this for any value of the h here, okay? So we want to develop a second order method for approximating f prime that uses the data f of x minus h, f of x, and f of x plus 3h only, all right? So we want to develop a method that has only these terms associated with the formula, okay, for f prime. So let's try that out. 3. So we need three things, right? We need f of x minus h, which we have up there in that list. So that is f of x, and alternation of signs. So minus h times f prime, plus h squared over 2 times f double prime, minus h cubed over 3 factorial f triple prime. And looks like we can just try with these terms here. So let's try here, let's put our error term as the third derivative, and let's see what happens. Of course, if we get stuck, we may have to add more terms up here, but hopefully that won't happen. F of x, of course, is just equal to f of x itself. And f of x plus 3h, well, what's that? Well, first term's f of x, plus, now it's just this 3h replaces that negative h, right? So 3h f prime plus, so this 3h replaces that h, so 3h squared is 9h squared over 2 f double prime, and then 3h replaces negative h, so 27h cubed over 3 factorial f triple prime of c. Okay. Not to mention, normally, so because the directions say develop a second order method, we know for f prime, if we want a second order method, remember that the error term will have an h squared in it, right? So if we're going to solve for like f prime, we know we're going to have to divide by h at some point, which means that it would be a good idea to go out to 3 terms, because if we divide this term by an h, we'll get an h squared, right? If we wanted a third order method, we would need one more term as our error, right? Because if we had the h to the 4th power term here, we'd be dividing by h, we would get an h cubed term for our error. That would give us a third order method, okay? So here we want to try to manipulate these things so that we can get a finite difference method that utilizes only these 3 terms and has second order accuracy. Okay? So let's see what we do. We want second order accuracy, so we want to keep any terms involving f of x because we need to have those in our formula. Of course, we want to keep these terms here because those are what we're going to solve for. Now, we don't need any second derivative terms, right? So what we're going to try to do is cancel out these guys. And then, of course, these terms are going to combine to give us our error. So what we want to do is try and cancel these guys. So we're going to have to perform a subtraction of some multiple of these guys, right? So let's see. I have 1/2 h squared here, and I have 9/2 h squared here. So if I take f of x plus 3h and take away 9 of these, right, if we multiply all these terms by 9 and subtract, these 2 terms will cancel out, right? So let's do that. F of x plus 3h minus 9 times f of x minus h equals. So let's look here. F of x, take away 9 f of x's. So that would be 1, take away 9, so let's say 1 minus 9 f of x. We'll have 3h f primes, take away negative 9h f primes, so that would turn to positive. So 3 plus 9h f primes. Okay. 9h squared over 2f double primes, take away 9h squared over 2f double primes is 0. Those will cancel out. And then lastly, we have 27 over 3 factorial h cubed f triple primes minus negative 9 over h 9h cubed over 3 factorials. So here we'd have a 9 over 3 factorial. Now we're subtracting a negative, so that's going to turn it to a positive again. So 9 over 3 factorial would be the coefficient there. We'd still have our h cubed f triple prime at c. Okay. So let's clean that up. This will be, so let's do the left-hand side again. Negative 8 f of x plus 3 plus 9 is 12 h f prime of x plus, so let's see, 27 over 3 factorial plus 9 over 3 factorial. That would give us 36 over 3 factorial. Well, 3 factorial is 6, so that would be 36 over 6, which is 6 h cubed f triple prime at c. Okay. Here I'm skipping the c1 and c2 deal here just for simplicity. We'll just consider c to be the same c. Okay. All right. So now we have it. All we need to do is just solve this guy for f prime. So we're going to add our 8 f of x's, and we're going to subtract our 6h cubes from both sides. So f of x plus 3h. I'll just put my 8 f of x's in the middle, and then minus 9 f of x minus h. It's customary to just write them in decreasing distance from x here. And subtract that guy. And that's going to be equal to 12h f prime of x. Dividing both sides by 12h yields our result. So f of x plus 3h plus 8 f of x minus 9 f of x minus h. That's my approximation over 12h. Minus, now 6h cubed divided by 12h will give us 1/2 h squared. So this is h squared over 2, f triple prime of c. Okay. So we can see that here is our finite difference formula that is approximates f prime and has order 2. Okay. So once again, we start with the Taylor expansions of the terms that we know should be there. We think about how many terms we need. If it's going to be order 2, we want to go to one more place than the order. And then we combine them to cancel out various terms that we do not need in our approximation, and then do some algebra from there. Okay. Last up, we can get finite difference formulas for the second derivative of f as well, right? So if we have these Taylor expansions, instead of canceling out the first derivative terms, we could cancel, or excuse me, instead of canceling the second derivative terms, we could cancel the first derivative terms and get a formula for f double prime. That is, whatever order that we want it to be. Okay. So let's see about how we do that. So we want the 3-point centered difference formula for f double prime of x. Alright. So it looks like our second derivative, here we have a 3-point centered difference formula. So if we know that, we're dealing with 3 points surrounding x, so we're going to utilize f of x plus h, and f of x minus h. So let's look at the Taylor expansions for those. These ones are simple. hf prime, h squared over 2f double prime, h cubed over 3 factorial f triple prime. Now, when do we know when to stop? Well, we know that we will. This method is going to be order 2. We've gathered that from the actual formula that's given here, right? So it's order 2. So we know at some point we're going to have to divide by an h squared to get the f double prime by itself. So we would need to go out to 4 terms to do that, right? So h to the 4th over 4 factorial f 4 prime at c. All right, so once again, this will be our error term. When we divide by h squared, we get an order 2 method. F of x minus h, same thing, it just alternates sides. So minus, plus, minus, plus. And of course, I'll use the same c, because as h goes to 0, c becomes, those c's become equal to each other. All right? All right, so let's look. What can we do here? Again, we want the formula to be solved for f double prime. So what we want to do is cancel out any f primes and any f triple primes, right? We don't want those derivatives in our formula, only these guys. So is that possible? Can we cancel both of them out? So what can we do with these two equations that are going to cancel these two terms? And you see it, we can just add them together, right? So f of x plus h plus f of x minus h equals, now let's go term by term, add these, we get 2 of them. Add those, are gone. Add these, we'll get h squared. Add these, they're gone. Add these, we'll get 2 h to the 4th over 4 factorials, f quadruple prime, and c. So, it's basically done for us, right? We can start to solve this thing now. So we want to get f double prime by itself, so let's take these two terms over. So we get f of x plus h minus 2 f of x's plus f of x minus h minus our error term. And what is 2 over 4 factorial? Let's look at that. Well, what's 4 factorial? 24. 2 over 24 is 12. So h to the 4th over 12. F quadruple prime c equals h squared f double prime. Alright, all we have to do is divide by h squared, so f double prime of x is equal to f of x plus h minus 2 f of x plus f of x minus h all over h squared minus our error term. So again, we're dividing this guy by h squared, so he's going to become h squared over 12 f quadruple prime at c. So we can use approximations for the second derivative. The second derivative will be approximated by this expression right here with this amount of error. It's second order, so we should expect it to be pretty good if h is small. Alright, so here are your exercises. You can go ahead and start working on those. If you have any questions at any point in the video, just let me know, and we can do a Google Meet or by email.